Alright, so let's revisit Newton's laws once again, except now we're going to revisit them within the context of torque. Okay, and basically we could rewrite all of Newton's laws and just substitute in torque for force and substitute in angular acceleration for acceleration. So our new first law is going to be that unbalanced torques lead to angular acceleration, just like unbalanced forces led to regular acceleration. So that's going to be our first law, rewritten for torque. Our second one is going to be that torque is directly proportional to angular acceleration. So as we increase our net torque, that increases our acceleration. And moment of inertia is inversely proportional to angular acceleration. So as our moment of inertia goes up, our angular acceleration goes down. And that's really going to lead to our equation for Newton's second law, the sum of the torques equals I alpha, which we'll look at in a second. And our last law is Newton's third law, that torques come in equal and opposite pairs, just like forces came in equal and opposite pairs. There is one caveat here. This is specific to torques. They're about the same pivot point, but in reality, we're not going to use this law quite as much. This is not going to be nearly as common, just because with forces, we had a lot of times where we had collisions between objects, we had objects interacting, and that's not going to be quite as common with rotating objects and with torques, although it will come into play sometimes. So here we have Newton's second law once again, the sum of the torques equals I alpha. That's what brings together a lot of the things we've been talking about, torque and moment of inertia and alpha. And the key here is figuring out that left side of the equation and thinking about what torques act on an object. Okay, that's going to be the key to all of these, just like figuring out what forces acted on the object when we were setting up our F equals ma. We now care about what torques act on the object. Let's go ahead and work through some conceptual problems with this. So starting with this first one, we have three rods which pivot about either their middle or their end, and we have the same force acting on each rod but in a different location. We want to rank the angular acceleration of the rods from greatest to least. So what we're thinking about with each one is sum of the torques equals I alpha. So in order to really determine that angular acceleration, we need to think both about our torque acting on each rod and our moment of inertia for each rod. So we're going to work through each one of those ideas one at a time. So for torque, we're thinking about the fact that torque is RF sine of theta. Each one has the same force. In each case, that torque is 90 degrees. The one thing that varies, though, is that radial distance, that distance from the pivot to where the force acts. So what we can say is we know the torque from A and B are going to be equal because it's the same force, same distance from the pivot, and both of them are going to be greater than the torque from C, which acts at a closer distance. Thinking about moment of inertia, we're really thinking about the distribution of our masses. We see that both B and C rotate about their end, whereas A rotates about its middle. Okay, keeping that in mind and keeping in mind that moment of inertia increases as there's more mass further from the pivot, B and C, which have all this mass that's further from the pivot than A, which rotates about the middle, are going to have a greater moment of inertia. So I can say that the moment of inertia for A is less than that of B, which is equal to C. Putting all of this together, I see that A has the biggest torque acting on it and the smallest moment of inertia, or tied for the biggest torque, I should say, which means that the angular acceleration for A is going to be greater than the other two. Moving on to comparing B and C have the same moment of inertia, but B has more torque, so B is going to be more than C. So there's my ranking. A is greater than B is greater than C. For this next one, I have a string wrapped around this disc here, connected to a mass, so the mass is going to fall, causing the disc to undergo an angular acceleration. Eventually, the mass hits the ground at time t, and the string releases, so I'm going to label time t here on my graph, call it that point right there. We want to draw the velocity versus time and position versus time graph for this. So at first, the disc is going to be speeding up from rest. So speeding up is going to be a curved line like this. I showed speeding up in the positive direction, but you could have done it the opposite way, and we'll look at that in a second. On the velocity versus time graph, speeding up would just be a positive slope here, increasing our velocity. Once time t hits, what ends up happening is our angular acceleration goes to 0. okay, because there's no longer a torque causing it to accelerate, but it continues moving, right? It doesn't stop moving. This is really a Newton's first law thing. So it's just going to continue with a straight line, increasing its velocity, but no longer having an acceleration. And on the velocity versus time graph, it becomes a horizontal line. If you wanted to flip your directions, what you would do is you would curve down, speeding up in the negative direction, and then hit your constant. And on the velocity versus time graph, a downward slope, and then a constant. Alright, moving on to some actual problems here, but first let's talk about a few tips with these. These really are going to be very similar to what we did with our F equals ma problems, except now it's sum of the torques equals I alpha. So we're going to want to draw a free body diagram to start setting up and thinking about what forces are acting on the object, but more importantly we also want to consider where those forces act. Okay, so this is going to be slightly different than F equals ma. We only cared about what forces we had before. Now we care about what forces we have and where they act. Two quick tips here. The force of gravity, in case you're curious where it always acts at the center of mass of the object. And the normal force and the force of friction, when we have those, they're going to act at the point of contact with the surface. And so we'll take a look at some of those examples as we move forward. Once we have our free body diagram drawn, we're going to want to set up our sum of the torques equals I alpha. This is really the key, that left side of the equation. We want to fill that in with the specific torques that are acting on the object in any given situation. We're of course going to be careful with our signs, considering clockwise and counterclockwise as our two directions, rather than up, down, left, right, but we still need to be aware of our signs. And sometimes we'll need to find moment of inertia. We're going to have formulas that are going to allow us to do that. Sometimes we're going to need to find angular acceleration with kinematics, and we've done that before as well. So let's go ahead and do a practice problem with this one. So we have a person exerting 400 newtons of force tangentially on the edge of a merry-go-round that has a mass of 50 kilograms and a radius of 2, and we see that force down here. In addition to that torque created by that force, there's also a frictional torque that pushes on the merry-go-round in the opposite direction. So we have this 400 Newton force, and what I usually do for torques is I go ahead and I draw them as curved arrows. So we have a torque from the pushing force going in the clockwise direction. We're also going to have a torque from friction, and we don't know exactly where that force acts, but we do know that it's going to act opposite to our pushing force. And so the thing that we're ultimately going to need to set up is sum of the torques equals I alpha. That's going to be our final step. But we're going to need to do a few other things first. So what I'm going to start doing is I'm going to start finding the things that I can find. I know that my moment of inertia is given by 1/2 mr squared because it's a disk. And so I can substitute in that mass and that radius. And I can solve for my moment of inertia, which is going to be 100 kilogram meters squared. Okay. The next thing I can do is I can solve for the torque created by this 400 Newton force. And I can do that by doing torque equals RF sine of theta, and so the torque is going to be 2 meters times the 400 newtons times sine of 90, because it's exerted tangentially on the edge of this merry-go-round. And so I get a torque here from the push equal to 800 Newton meters. The other thing I can do is I can set up my kinematics. I know it starts from rest and reaches a speed of 15 radians per second. Over a period of time of 3 seconds, and so I can use that to go ahead and solve for my angular acceleration. So 15 equals 0 plus alpha times 3, and I get that my angular acceleration is 5 radians per second squared. Now that I have all of that basic stuff, I'm going to use the equation that brings everything together. Sum of the torques equals I alpha. So I can take my I that I solved for, I can take my alpha that I just solved for, and I can take one of those torques I just solved for, and I can bring it all together. The key, just like with F equals ma, is setting up that left side. So what torques do we have acting on the object? We have the torque from the push and the torque from friction. So I'm going to say that torque from the push minus the torque from friction is going to be equal to my moment of inertia times my angular acceleration. I did choose to make this be the positive direction and make counterclockwise a negative, which is opposite the normal convention, but as long as you're consistent, that's what's important. Okay, and so I'm also going to make my angular acceleration positive, because whatever direction my pushing torque is going, that's also going to be the direction of my angular acceleration. So what I end up getting is 800 minus this torque from friction, which I don't know, equals 100 times 5. And so I get that my frictional torque is going to be equal to 300 Newton meters. For part B here, the person now stops pushing. We want to know how long it's going to take for the merry-go-round to slow to a stop. So I'm going to set up the sum of the torques equals I alpha once again. Now the only torque that I'm going to have acting on it is that frictional torque going opposite its motion. So I can say that that frictional torque is going to be equal to I alpha. I know that torque is negative 300 Newton meters. So that's going to be equal to I, which is 100 times alpha. And so I get that my new angular acceleration is going to be negative 3 radians per second squared. Once I have that, I can use kinematics once again to go ahead and solve for how long it's going to take to come to a stop. So it's rotating at 15 radians per second. It's eventually going to come to a stop, and it's slowing down at a rate of negative 3 radians per second squared. So it's going to end up being the same equation I used before to solve for my angular acceleration, but now I'll just solve for time. And what I end up getting is that my time here is going to be equal to 5 seconds. Moving on to my next two questions here. So part C asks how many times will the merry-go-round rotate total, both while speeding up and while slowing down before coming to a stop. So what I'm really looking for there is what is my total delta theta. Okay, how much do I rotate? So what I'm going to do is I'm going to bring over my kinematics charts from part A and B of this problem. So there I have my charts both for the speeding up portion of this and also for the slowing down portion of this. And so the first thing I'm going to do is I'm going to try and solve for my delta theta. So delta theta is 1/2 omega initial plus omega final times t. So if I sub in for the speeding up portion, we have 0 plus 15 times 3, which means that my delta theta is going to be 22.5 radians. I can now go ahead and do the same thing for the slowing down portion. So for that, it's going to be 15 plus 0 times 5 seconds. And so I get that while slowing down, my angular displacement is 37.5 radians. I now can combine those two to get my total angular displacement, which ends up being 60 radians, except we want how many times does it rotate. So I need to go ahead and convert. I know that one rotation is going to be 2 pi radians, and so those radians cancel out. And what I'm left with is 9.55 rotations, which is the equivalent of 60 radians. Last thing we want to do is we want to draw the position versus time and velocity versus time graph for this. So speeding up is what's going to be happening initially, so that's going to look something like that on my position versus time, and something like that on my velocity versus time. After that point, that's where we stop pulling, so that would be at 3 seconds. I'm going to start slowing down, eventually coming to a stop. So that means this final time here is 5 seconds later for a total of 8. And on the velocity versus time graph, I'm slowing down to a stop, going back to 0. And so there's my 8 seconds. As always, I could flip those graphs, and so if it looks something like this, that would be acceptable, but then your velocity graph should match and look something like that. Alright, for this next one, we have a person that pulls tangentially on the edge of a fixed bike wheel with a force of F, so there's our force there like that. The wheel has a massive M and a radius of R and can be approximated as a thin hoop, and we are going to assume that there are no other forces creating a torque, so the only torque here is going to be from that pulling force. And so we want to first figure out what is the angular acceleration of our wheel. Okay, so we're going to start with sum of the torques equals I alpha. In this case, the only torque we have is the torque from that pulling force, and that's going to be equal to my moment of inertia here, which for the wheel is mr squared, times alpha, my angular acceleration. I'm going to take a second to solve for that torque from the pulling force, which is just going to be RF sine of theta. Okay, so the distance from the pivot, which is at the center of the wheel here, is just going to be that radius of the wheel. I know my force is just F, and the angle here is going to be 90 degrees because that's the angle between my force and that R value. So I can substitute in just RF for that torque from the pulling force because sine of 90 is just 1. And so that's going to be equal to mr squared times alpha. One of the r's on each side is going to cancel out. And I find that F over mr is equal to my angular acceleration. For part B, we want to know how long it will take. So for that, I'm going to consider kinematics. The wheel starts from rest and reaches an angular speed of omega, accelerating at a rate of F over mr. So I can go ahead and set up my omega final equals omega initial plus alpha t equation. And I end up getting that omega equals 0 plus that F over mr times t. And when I solve for my time there, I get that my time is going to be equal to mr omega divided by that force. And then for part C, we want to know if the radius is doubled, by what factor does the angular acceleration change? And so I'm going to set up, I'm going to use this equation here and set up an A prime, my new angular acceleration. And so that's going to be F over m times 2r. And so I'm going to pull that 2 out from the bottom. And since it's on the bottom, it really gets pulled out to become a 1/2 times F over mr. Okay, which is just my original angular acceleration. So that means that my new angular acceleration, A prime, is just going to be 1/2 of my original. So that would be the factor by which it changes. Up next here, we have a wooden beam that's connected to a hinge, and it's initially released from this point A here, and it swings down to point B. And we want to first draw all the forces acting on the beam after it's released. So the one force we're going to have is gravity, and we know that gravity always acts in the center of objects. So there's my FG there. And when it swings down to B, it's still going to act in the center of mass of the object, which is just going to be directly in the middle, since we'll assume it's a uniform beam. We're also going to have another force acting on the object, and the way you can think about this one is if there was just gravity acting on it, this thing would fall straight down. Why does it not fall straight down? Because of this hinge here. So there is another force here from the hinge, and that's going to hold this beam up, or at least hold the left side of that beam up. Okay, so those are going to be the forces acting on it for part A there. We now want to go ahead and determine the angular acceleration of the beam in position A. So I have drawn up here a free body diagram for position A, and we're going to think about the torques acting on it. Now, the pivot is right here, okay, on that left side. So that means that there's no torque here from the force from the hinge, and we simply have a clockwise torque from the force of gravity. So setting up my F equals ma, it's going to be just that torque from gravity equals I alpha. I'm just going to say that clockwise is a positive direction in this case. I can substitute in RF sine theta for that torque from gravity. I know that my moment of inertia is given here as 1/3 ml squared times alpha. My R, that location where gravity acts, is going to be from here to here, that distance from the pivot to where that force acts, which is half the length. So I'm going to call that R L over 2. The force of gravity is just going to be mg, of course, and it's going to be sine of 90, which is 1, equals 1/3 ml squared times alpha. And we're going to go ahead and we can cancel out the m's. We can get rid of one of the l's here. That sine of 90 just becomes 1. And so what we end up getting is g over 2 equals 1/3 L, and they're actually using a capital L here for the length. So 1/3 L times alpha. And when we solve for our angular acceleration, we get that that's going to be equal to 3g over 2L. Moving on to that final part, we want to solve for the angular acceleration at point C. So thinking about that point, and the sum of the torques equals I alpha, there's no torque here from the force from the hinge because it acts on the pivot. And that force of gravity, if we think about our R here, that line from the pivot to where that force acts, and the direction of that force, we see that the angle between them, depending on how you look at it, is either 180 or 0. Either way, the torque from gravity is also 0. So that means we have no net torque acting on this object, and so of course its angular acceleration for this situation is just 0.